Hello, welcome to the second lecture on of the course. Today we will talk about the undamped free vibration of a single degree of freedom system. In the last lecture, we have talked about the degrees of freedom, how to derive the equation of motion, the various methods by which we can derive the equation of motion. We have also solved certain problems to derive example problems where we have derived the equation of motion for several single degree of freedom system. So, the next topic therefore is how to solve this equations of motion that we have derived earlier and how to find out the response of the system under free vibration condition and how to analyze them. So, let us go back to the very elementary example of a spring mass system, where I have a concentrated or point mass m. It is connected with a linear spring k, and it is connected with a linear spring k, and then the displacement is the horizontal displacement u t, and the equation of motion, this we have already derived in the last class. So, this equation of motion has a term f t. Now, in this class, I mean in this lecture, we will talk about the case when f t is equal to 0. Therefore, there is no external force that is applied on the body and it becomes a free vibration problem. So, how will the system vibrate if there is no externally applied force? The vibration will happen due to some excitation in forms of initial condition. So, at t equals to 0 or at a certain time instant, we will give some displacement or or velocity to the body, and because of this condition, this excitation, the body will start vibrating about its position of equilibrium. So, it will start, this is its position of equilibrium, and it will start vibrating from that position. Okay. So, let us write down the equation for the single degree of freedom system without any force, or a free vibration equation. So, you can see that this is this equation is a very simple equation. It is a linear equation, it is a second order equation, it is homogeneous because of the right hand side being equal to 0, and we very much know how to solve this kind of equation. Okay. So, first job therefore is to solve this equation to obtain the expression for u t, to obtain the solution for u t. That is what we are going to do. We are going to solve this equation so as to find out u t. That is what we are trying to do. Okay. So, let me just rewrite the equation in the form. So, I have m u double dot plus k u equals to 0. So, let me just rewrite it in this form, equals to 0. So, this k by m, let me say that k by m is equal to omega n square. As of now, just think that omega n is any arbitrary parameter, and I just define k by m equals to omega n square. Therefore, my equation becomes u double dot plus omega n square into u equals to 0. Okay. So, now how are we going to solve the problem? Let us assume, so we all know how to solve this problem. So, one way to solve is to assume u t equals to e to the power lambda t. Okay. So, if we assume u t to be e to the power lambda t and substitute back into this equation, and then if we substitute back, then we get an equation something like this, okay, where we have lambda square e to the power lambda t into omega n square e to the power lambda t equals to 0. Now, since e to the power lambda t cannot be, equal to 0, okay. So, the other equation, that is lambda square plus omega n square is going to be equal to 0, and the solution of that is lambda equals to plus minus I omega. Okay. So, okay. So, now we have derived that lambda is equal to, sorry, we have derived lambda equals to plus minus I omega n. So, if this is the solution for lambda, then the generalized solution of this is going to be ut is equal to C1 e to the power I omega n t, that is one root, and then I have C2 into e to the power minus I omega n t, that is the second root. Okay. So, this can further be written as C1 plus C2, okay, into cos omega n t plus I C1 minus C2 into sin omega n t. I have done nothing but just expanded this solution. Okay. So, the two unknowns that we have in this solution is my C1 and my C2, and I have to solve for C1 and C2 from the initial conditions. Therefore, I need the initial conditions to solve for C1 and C2. Okay. So, as I said earlier, the initial condition will either be the displacement at t equals to 0, okay, when the vibration initiates, and let me give a very generalized parameter symbol for this. So, let us say ut at t equals to 0 is equal to u0, and the displacement, the velocity at t equals to 0, that is u dot t at t equals to 0, let us call that as u dot u0. Okay. So, I have this two condition. Let me plug this in to this solution, the generalized solution that we have got it. Okay. So, if we plug this into this solution and if we solve it, we will actually get ut is equal to u0 cos omega n t plus u dot 0 by omega n into sin omega t. I am skipping a couple of steps in between, but these are very easy. One should be able to derive this. Okay. I am just plugging these values into this expression, and I am expressing C1 and C2 in terms of my initial condition, that is u0 and u dot 0. Okay. And therefore, my response finally becomes like this. Okay. So, my response due to initial condition, my free vibration response. So, this is the free vibration response. Okay. Free vibration undamped response. I have yet not considered damping. So, free vibration and undamped response ut is going to look something like this. Okay. So, now let us use basic trigonometry, and we can write this as a cos omega n t minus phi. Okay. So, where omega n, I have earlier taken it as omega n square was taken as k by m. So, omega n becomes root over k by m. Okay. So, now what do we see? So, this equation, just by some trigonometric manipulation, we can always write it in this form, where omega n is square root of t k by m. A is equal to the amplitude, which is going to be u0 square plus u dot 0 by omega n whole square, and phi is going to be So, phi is going to be tan phi is going to be u0 dot by u0 into omega n. Okay. So, this is what we are going to get as tan phi. Okay. This is what we are going to get as tan phi. Now, we can see that u0 is becoming a cos omega n t minus phi, where I know the value of omega n, I know the expression for phi, I know the expression for a. Therefore, a single degree of freedom system under initial condition and without any externally applied force is going to vibrate as a sinusoid with a time period t n, which is going to be 2 pi by omega n. Okay. Therefore, a single degree of freedom is going to vibrate with a frequency of omega n. Therefore, this omega n is called the natural frequency of the system. Natural frequency of the system. And A, which is the maximum value of the response ut, is called the amplitude of the response. So, this is A and this is called the amplitude of the response. And phi is called the phase angle or phase angle of the response. Okay. And this initial thing is the displacement at t equals to 0, which is going to be, if you put t equals to 0 there, you will see that this is going to become u0. Okay, or the initial displacement of the system. This is the time axis, I forgot to mention, this is the time axis and this is the displacement axis. Okay. So now therefore, we know how to find the response of the single degree of freedom system under initial condition and under no externally applied force. Okay. So, let us now solve certain problems. Let us now solve certain problems to obtain a better understanding of the concepts that we have just now talked about. Okay. So, let us consider again a simple single degree of freedom problem, a spring mass system. The mass is being m and the spring is k, and a bullet of mass small m and velocity v is going to hit this mass with and stick to this mass. So, one can easily appreciate that when a bullet with a velocity v comes and hit this mass and sticks to the mass, this mass will start oscillating. So, what we have to do is to find out the resulting oscillation or vibration of this mass after the bullet has hit the body. Okay. So, let us we already know that the equation of motion of this before the bullet hit is mu double dot plus k u is equal to 0. Okay. But the vibration is going to start only after the bullet has hit the mass and the bullet has stick to the mass. So, the equation of motion actually is m plus small m. So, then after the bullet hits this mass actually now becomes a capital M plus small m. Okay. So, we will have capital M plus small m, which is going to be the new mass, and then we have mu double dot plus k u is equal to 0. This can actually be written as u double dot k by m plus m into u is equal to 0 and omega n square is going to be root over k by m plus n. Okay. So, the solution of this equation we have derived earlier is going to be ut, which is going to be u0 cos omega n t plus u dot 0 by omega n into sin omega n t, where omega n is nothing but square root of k by m plus m. That is the natural frequency of the system. This is the natural frequency. Okay. So, now we have to figure out what are the initial conditions of the system. Once we know what is u0 and what is u dot 0, we can easily find out the total response of the system. So, our next job is to find out the initial conditions. Okay. So, the initial conditions u0 and u dot 0. Okay. So, u0 is going to be 0 because there is no initial displacement imparted to the mass m. Okay. But what is u dot 0 is not going to be equal to 0. So, how are we going to find out u dot 0? To find out u dot 0, we have to use conservation of momentum. So, we have to use conservation of momentum because once the bullet hit the mass m, it imparts certain velocity to the mass m plus m, and we have to find out that velocity. So, therefore, by conservation of momentum, capital M plus small m into u dot 0 is going to be small m into v. So, that is going to give me u dot 0 is equal to mv by capital M plus n. Okay. So, now our problem is solved. We have got u0 equals to 0, we have got u dot 0 equals to mv by small m plus capital M. So, we have to just put this into this equation. I mean that's only our job. So, we have to put this initial condition into this equation. Okay. And if we do that, then we get the response, final response as ut, which is equal to mv by small m plus capital M into sin omega n t. So, this is the answer of the problem. So, this is the response, this is the answer of the problem. Okay. So, let us now go to the second problem. Okay. So, second problem is slightly more difficult than the difficulty level is slightly higher than the previous problem. So, what we have here is again a spring mass system, but here it is suspended in the vertical direction. Okay. So, I have a capital mass m, which is basically, so this is basically an electromagnet. Okay. So, this electromagnet is used to lift scrap, iron scrap in an industrial area. So, this is a real problem where this kind of application is very commonly seen. So, this electromagnet is used to lift this scrap small m. Now, what happens is that, so at t equals to 0, so initially this scrap is attached to the electromagnet, and at t equals to 0, the current in this electromagnet is stopped. Okay, and as a result, this scrap falls off. So, you can also appreciate that as soon as the scrap falls off, the mass m is going to start vibrating. Okay. This can be visualized very easily, right. As soon as we drop this scrap, you can visualize that this capital M mass is going to start vibrating. So, what we have to do is we have to find out the response, okay, when the current is switched off and the scrap is dropped. Okay. So, that is what we need to do. Okay. So, let us see why this vibration is going to happen. Okay. So, this red color line, this red color line is the, so this red color line is the unstretched position of the spring. Okay. Let us just take it as a reference point. Okay. And then this is the static equilibrium when the scrap is attached to the static equilibrium position when the scrap is attached to the mass. Okay. Now, when the scrap is unloaded, then the mass will move up and it will go to a new static equilibrium point. So, this is our new static equilibrium point. So, this is our new static equilibrium point that the mass will reach after the scrap has been dropped off. Okay. So, at t equals to 0, this is where it was, and when the current is switched off, it is going at this location and the vibration will start about this location. So, it will start vibrating about this location. Okay. So, let us now try to solve this problem. Okay. So, how are we going to solve this problem? Again, the equation motion is m u double dot plus k u is equal to 0. Therefore, the response after we solve the problem is going to be u t, which is going to be u 0 cos omega n t plus u dot 0 by omega n sin omega n t, where omega n is nothing but square root of k by n. Okay. So, now our job is to find out the initial conditions. So, we have to, so to solve the problem, we need to find out the initial conditions. Okay. This initial conditions u 0 and u dot 0. So, once we know u 0 and u dot 0, we will get the expression for this response. So, u dot 0 is going to be 0. Because at t equals to 0, there is no displacement, that is no velocity that is applied to the single degree of freedom system. What about the initial displacement? So, we need to find out u 0. So, what is going to be u 0? So, u 0 when the scrap is attached, so we are measuring u from the unstretched, measuring u from the unstretched position of the spring, unstretched position of the spring. Okay. So, u initially, let us call that u1, okay, was k by capital M plus M. This is when the scrap was attached, okay, right. So, it was in the static equilibrium position of the body. So, u1 measured from the unstretched position of the spring is k by capital, sorry for this, it is M plus small m by k. So, ku is going to be mg, right. So, mg, so this is going to be m plus capital M plus small m into g by k. Okay. So, let us measure the second one, which is when the scrap was dropped. So, let us measure. Okay. So, then the scrap is dropped, so only mass is capital M. So, it is mg by k. Okay. So, this is the new position of the mass when the scrap has been dropped. Okay. So, the overall displacement that happened at t equals to 0 with respect to the unstretched position of the spring is going to be u1 minus u2, which is going to be small mg by k. So, this is going to be the overall displacement that the mass m has experienced at t equals to 0. Okay. So, therefore, we can call this to be our initial displacement u0, okay, and then we can say that the response is nothing but because u dot 0 is equal to 0, there is no initial velocity. So, u0 is obtained in this form. So, this can actually be written as mg by k into cos omega n t. Okay. So, this is the response of the system. So, this response u0 is being measured from the unstretched position of the spring. So, this response is from the unstretched position of the spring. You can also find it from the stretched position of the static equilibrium position of the spring as well. Okay. So, I leave that part to you. Okay. With this we come to the end of the second lecture on the course. In the third lecture we will talk about damped free vibration of single degree of freedom system. Thank you.